Typing a program in from a book could be both frustrating and rewarding. The Aquarius program book by Peter Good can be found in the Internet Archive and also in the Mattel Aquarius users group on Facebook. On page 45, I found a program in here that I thought would be useful called the Morse encoder. This program takes a line of text and converts it to Morse code. This program is only 18 lines long if you leave out the remarks, but a novice basic programmer would immediately encounter some words that are not familiar. The author of the program has typed in valid basic commands, but he's left the spacing out between the commands, probably to save on memory, since the Mattel Aquarius had a dismal amount of memory if you didn't have the expansion cartridge. Now, the interpreter in the Aquarius can easily read this, but not so much a human if he was a novice at basic. So in line 720, for example, it doesn't read form equals 1 tolen. It reads for m equals 1 to the length of f string. Today we have the luxury of using Notepad to type this program in. So let's type it in using the appropriate spacing between the words. Bring up a Mattel Aquarius emulator and run the program. Now here I've already typed it in. We'll bring up the emulator. There are two. There's the virtual Aquarius and there's Aqualite. I'm going to use the virtual Aquarius first. We will bring the file in using the quick type command. And we'll run it and see what happens. Message to transmit. The cat in the hat. I didn't get that. That doesn't actually sound like Morse code to me. No. How about I have no idea what that was. I got that. I got that. I got that. But when you type them together, you get that. Okay, that does not sound like Morse code. Now the book says you can change variable s to slow the program down. Let's give that a try. Line 20. S equals, we'll double it, 24. D equals 2. The cat in the hat. That's slower, but it doesn't sound like Morse code to me. Okay, let's see what's going on with this program and figure out some way to fix it or improve it. So we'll go through this line by line. S equals 12 is a variable that's used in the sound. So we have sound 12, 100. And the format is the duration and the tone. D is equal to 2. That's used in the delay between the words. So we have for W equals 1 to 120 times D, or W equals 1 to 240. The way a delay is created between the letters and the words is to have the computer stop and count. In this case, for a long pause, it counts from 1 to 240. For a short pause, it counts from 1 to 100, then continues on with the program. Line 30 creates an array in memory of 26 elements. Now this is how I visualize it, as a table with 1 row and 26 columns. Each column is actually an element in the array in which you can put data. To get the data into the array, there are 26 read statements. The data comes from the bottom of the program. For the 26 times that the program is looping and reading data into the M-string array, there has to be an item of data. Each item is separated by a comma. So as the information goes into the array, I picture it looking like this. So that M-string at 1 is SL. M-string at 2 is LSSS, etc., until all 26 elements of the array are filled. So what is this data exactly? We'll make it a little bit larger. So we have data SL comma, LSSS comma, LLS comma. Well, these words spell that sounds like snake talk. That sounds like a serpent. That's the serpent tempted me to buy a new microphone because the one I'm using was literally 98 cents. So do we have any English words that actually start with well, how about slap, 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 slap. Well, this is actually Morse code. The author of the program decided he would use S for short and L for long. So the letter A in Morse code is dit da, or in this program it's short long SL. B is da dit dit dit. In this program it's long short short short. When I was typing this in, I found a mistake. This is the Morse code for A, B, C, D, E, F, and G. But if G is LLS, how can C be LLS? So the mistake is in the letter C. It should be LSLS. Line 40 clears the screen and prints message to transmit. Line 50 asks for your input and saves it in a variable called iString. The next line starts a loop that goes from 1 to the length of iString. So if you type in the cat in the hat, you've got 14 characters and 4 spaces. So the length of iString would be 18. It would be for L equals 1 to 18. Line 70 looks at each individual character of iString, which in this case is the cat in the hat. If the characters are not between A and Z, it goes to 300, which says pause between words. The computer will then count from 1 to 240 and return. And the logic is if it's not a letter, it must be one of the spaces between the words. The program will not go to 90, which says transmission complete, until it is done looping through all 18 characters of the cat in the hat. Line 80 takes each individual character of iString, once again iString is the cat in the hat, and assigns it a value of xstring and goes to 700. 700, even though it says sound 1 character, it's not there yet. 710 takes the ASCII character code of xstring and subtracts 96 from it. Because the ASCII character code of the letter A is 97, if you subtract 96 you get 1. The ASCII character code of B is 98, you subtract 96 and you get 2. So basically it assigns the numbers 1 to 26 to the 26 letters of the alphabet. So X is equal to a number between 1 and 26 that corresponds to whatever letter is being parsed in iString. All this really does is take the letters of the alphabet and assign them a number between 1 and 26. Now we have F-string. F-string is equal to M-string at X. M-string is our data. If X is equal to 1, then F-string is equal to M-string at 1, or the Morse code equivalent of the letter A. Here's another way to visualize it. I-string is equal to the cat in the hat. X-string is equal to the individual letters in the phrase the cat in the hat. X is the numerical equivalent of the letters. And F-string at X is the Morse code. The next 2 lines start looping through F-string. Now remember, we're already looping through I-string, which is the phrase the cat in the hat. Each individual character in F-string is extracted. If it's an S, it will go up to line 500 and sound out a dot. If it's not an S, it ignores this. It goes to 600 and sounds out a dash. When it's done looping through F-string, it returns to the main loop of I-string. Okay, now we're back to the program at line 300, which is a remark. Line 310 is a pause where the computer counts from 1 to 240. Line 410 is a shorter pause where the computer counts from 1 to 100. Line 510 is the sound of the dot. Line 610 is the sound of the dash. The program will continue to loop until all the characters in iString have been parsed and turned into Morse code, in which case it will then go to 90. Line 90 says print the words transmission complete. There's a short pause, and then the program runs again, asking you for a message to transmit. There's a lot that can be improved upon in this program. As a matter of fact, while the program is executing, it looks something like this, going back and forth and up and down and calling subroutines. I think we can compact the program and actually get it to sound like Morse code. Here's our original program, and here's the updated program. I've put some spaces in here to make it easier to read, but they would be ignored by the Aquarius. These two variables, S and D, have been removed because instead of having the computer perform a calculation, just put in the numbers that we want. That is the same for both the sound and the delay. These three subroutines are no longer subroutines. I wasn't able to move this one. If we take this code and copy it to where it's called from, it's perfectly valid code, but it exceeds the length of the line allowed by the Mattel Aquarius and causes an error. So we'll undo that edit. The data statements have been changed to dots and dashes. It seems a lot more logical than using S's and L's. But the real fix to the program was to add a small delay between the dots and dashes. Now, the original program had a delay between the letters and another delay between the words, but no delays between the dots or the dashes. Adding the delay in makes it much easier to read the Morse code. Another improvement to the program is that it will type out the letter and the Morse code equivalent as it's progressing through the sentence or the phrase that you've typed in. Now let's pull the program into the Aquarius emulator and see if it works any better. Once again, we'll use the quick type command. Run. Message to transmit. The cat in the hat. Well, that sounded pretty good, but just to make sure, let's bring it up in Aqualight and see how it runs there. Message to transmit, the cat in the hat. It runs a little faster in Aqualight. Aqualight's a newer emulator, and I think it's still being supported, so we'll use Aqualight from now on. Now let's see what happens when we put in some numbers. A, B, C, 1, 2, 3, D, E, F. There are no numbers because we haven't programmed any numbers into it yet. So here's the next version. We've added 10 digits. We've increased our array by 10. It used to be 26. Now it's 36 with 36 read statements. And here are the 10 digits in Morse code. We also had to add this message here to get the correct ASCII character code. Another thing that needs to be addressed is line 70. We won't be able to type any numbers in because line 70 looks for letters between A and Z. So we'll remove this limitation. We'll make it say, if you see a blank, then go sub 300 and pause. But now since the line is shorter, we can actually put the subroutine on the line. We can get rid of the subroutine and make the program more efficient. Okay, so let's give that a try. ABC, 1, 2, 3, DEF. Okay, that works pretty good. There is still one improvement we can make. Suppose a user types in something other than a lowercase letter or a number. Suppose he types in a couple pound signs and a dollar sign by accident. ABC and an uppercase ABC. What do we get now? All right, obviously it doesn't like anything other than a lowercase letter or a number. So we'll fix that in the next version. On to the next version. Version 8 contains a message telling the user to only enter numbers and lowercase letters. Of course, that's not going to stop the program from crashing if he enters some garbage in. So an additional array of 36 elements has been added with 36 read statements and 36 data statements containing a list of allowed characters. As the program goes through converting the numbers and letters into Morse code, it checks each one against this list. If it's not on the list, it just ignores it. So let's give that a try. This is version 8. There's our list of allowed characters at the bottom. Okay, message to transmit, ABC, garbage, 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 uppercase ABC, and 1, 2, 3. That worked pretty good. It just ignored everything that wasn't on that list of allowed characters. Version 9 is the same as version 8 with some enhancements. There's some colors in it, and it prints a space after each word. We'll give that a try. Load the file, version 9. That looks pretty good. I like how the word "the" sounds like shaving a haircut. Now this is something that an actual radio amateur would type in. Those call letters once belonged to a friend of mine back in the 80s. I think that works very well. I can think of another enhancement. You can have the program ask the user how many words per minute he wants to transmit, 5, 10, 15, or 20. You can then use some if-then statements to change the timing between the pauses and the dots and dashes. You get kind of obsessed with this. I wonder what else is in that book. I've been playing with this program for 3 days. Don't forget to call our bulletin board from 1991. By the way, this microphone really did cost 98 cents.